shall consider the concept of ordinary differential equation in resolving first order differential problems. Can be likened to modeling problems of the first order or application of first order to solve challenges or problems in sciences and engineering. As you can see, the concept of ordinary differential equation was a methodology for solving problems that has variables. For example, if we talk of dy dt is equal to 2, what you have just expressed is a velocity function. Perhaps you are saying that the velocity of a moving vehicle is 2 meters per second. That is dy dt equal to 2. You have just been able to form a first order differential equation that is non-homogeneous and that can be solved by separation of variable technique. So if you say dy dt equal to 2, that means the velocity of a moving object is 2 meters per second in terms of application of ordinary differential equation. A first order differential equation has been formed by writing y prime function of t equal to 2, which implies dy dt equal to 2. So therefore, separation of variable techniques implies that dy is equal to 2 dt when differential t multiply both sides. So if we integrate dy and integrate 2 dt, we now finally have y is equal to 2t plus arbitrary constant c. If it is an IVP problem, initial value problem, you'll be given the value for y and also be given the value for t. When substituted into the general equation, you will now get the value for c, and that gives us the general particular solution. But if it is written as y is equal to 2t plus c, that is general particular equation, because it is containing an arbitrary constant c that has not been converted to a particular value of c. Now, if a particular value of c is gotten, it becomes the general particular solution. Furthermore, according to eminent scientists and engineers, they proposed some conceptual formulas that can be linked to resolving problems that has to do with first order differential equation. The likes of these eminent personnel are Sir Isaac Newton, Kirchhoff's, Laguerre's, Einstein photoelectric equation, and many others. The voltaic cells will also relate to Thevenin's. Most of these eminent scientists and engineers, their applications cannot be left out, as to date they are still being used in solving problems in engineering and mathematics and sciences generally. For example, when we have the spring is a mechanical object. When mass is inserted into a spring, it tends to distend even to a breaking point or a yielding point. That concept was first resolved by Hooks. That is to say, the force on the spring is equal to kx. Now, because of the distension or the extensivity, we can introduce a minus sign, which is showing that it is going against the gravitational force of attraction by the methodology of pulling the string. Now, that is an opposition reaction. At that level, mass times acceleration is equal to minus kx. So, acceleration, as it were, can be given as d square x dt square if it is rectilinear in terms of the plane of the object. If you also make it a vertical implied concept, then that is to say it is m d square y dt square, which is equal to minus kx. So a second order differential equation has been formed by that Hooke's law, which states that the force on a string varies directly to the extensivity of the spring. The extensivity can be denoted as E or X. or also y. So these are ways you can form differential equation by applications of laws in science and engineering. So also, when we look at the concept of motion, whereby mass times acceleration is equal to kv. kv, that is to say, you are observing a motion that has implication with the atmospheric resistance. And the atmospheric resistance, when we consider the frictional effect of the atmosphere on a falling object, you see it comes to play. It comes to play because there are two forces that will come to play there: the effect of gravity on the object and also the effect of air resistance to the motion of the object. So we can now have m d square y dt square is equal to mg minus kv, where kv is offering resistance to the motion of the object. Take note that this concept varies. It could be minus mg based on the question. So and so, you have a lot of related concepts, even in electrical engineering, where the total voltage drop in a circuit has to be V subscript T is equal to voltage across the resistance and plus voltage across the capacitance, and sometimes voltage across the inductance. That is to say, you are going to have a relationship of L di dt plus the voltage across the capacitance. The voltage across the capacitance, as you know, is what you have to impute the value for the voltage across the capacitance, and also you also impute the value for voltage across the resistance, which is based on Ohm's law. Ohm's law. So when we have this relationship integrated in a circuit system, you can have the value for the charge or the value for the current as the question lies. So in other words, you can also use MATLAB coding to draw the graphs of this implication. Now, we could also apply the method of first order differential equation to resolve problems in population and mixture of water in a tank. Population of a country, for example, Nigeria, when you are expected to model the population of the country, what you will have is dp dt, that is to say, the population, the time, because every moment, every second, minute, hour, days, children are being given birth to. So also people are dying. So what happened in population relationship is to derive a differential equation model that satisfies a differential equation. And a differential equation, as it were, there must be differentiation expression. So we have dp dt is equal to change in the population. Change in the population. Now, what we do is to the change in population becomes the constant multiplied by the population itself. So that is to say that dp dt is equal to gamma p. Gamma p, where gamma is a constant concept which is subject to deterioration or increment because it's equal to the difference between the birth rate and the death rate multiplied by the population. That gives you the rate of assessment of the population of a country. So dp dt is equal to gamma p. So if you are to solve it mathematically, you are now going to collect the variables. The variables is that differential p will stay, and p from the right hand side will be dividing both sides to be dp over p is equal to gamma dt. when it is integrated, you have natural logarithm of p is equal to the integral of gamma t dt, which gives you gamma dt, gamma integral dt rather. So gamma integral dt gives you gamma t plus arbitrary constant c. And that is to say, you have lim of p is equal to gamma t plus arbitrary constant c. When exponented based on Napierian logarithm, the exponential logarithmic concept, you now have that p is equal to exponential function of gamma t plus arbitrary constant c. So also you have the mixing problems, and numerous of them too. And there are cases whereby you now use the Bernoulli's equation to resolve, or the Riccati's analysis. So some of these issues can easily be resolved using first order differential equation. But the other reference I made, which is the total voltage in a circuit considering the voltage across the inductor, voltage across the capacitor, and voltage across the resistor, that concept is purely a second order circuit or second order differential equation model. But a first order differential equation model can be generated from total voltage in a circuit of resistor capacitive circuit, inductor capacitive circuit, or otherwise. It has to be two at a time. Then you can now generate a first order differential equation. However, differential equation models can metamorphose to second order after first order differential equation, and even to third order to resolve certain engineering problems. So differential equation is applied in resolving life challenges. Even the radioactive decay system, for the radioactive substance to decay, to deteriorate, it is also a function of first order differential equation. Assuming the radioactive substance is denoted by letter R, that means the rate of decay of the radioactive substance is the R dt. When it is the R dt, it means the rate of deterioration, the R dt, varies directly as the radioactive substance, which is R, capital letter R. Now, if we remove the sign of variation, we are going to have the R dt is equal to minus KR. The minus is an indication that it is a deteriorating function, meaning that you are now going to resolve this the R dt equal to minus RT using first order differential equation model, which is quite simple. All we do is to multiply both sides by dt, and that gives us the R is equal to minus, on the right hand side, if you choose to use alpha as your constant, use k. Okay, we are using k, it gives us minus k dt multiplied with r. So since you are integrating with respect to t, it means integral dr is equal to minus k integral r dt. If you integrate, you are now going to have r is equal to minus rtk, minus rtk, or minus tr. So at that level, k is a fundamental factor which is attached as a constant. Then the rate is also on the right hand side. So it now gives you minus kRt plus arbitrary constant c. Now, of course, it is obvious that that relationship in the heights of mathematical concept will not fly. Why? Because R has a variable, and that variable has to be separated. So the initial work done was actually a layman's approach into solving problems. You do not integrate R when it has a family on the other side. So rather, what you do conceptually is to start ab initio, say, okay, dr dt is varying directly as R. Introduce the constant of proportionality, which is negative, to give you the R dt is equal to minus KR. Now we use the method of separation of variable. You can see that the initial operation set does not fly, does not work. Why? Because the normal concept of collection of item or separation of variable is very key in ordinary differential equation. That is to say, we bring the y from the right hand side to the left hand side by dividing through with r, and that gives us integral dr over r is equal to minus k dt. Minus k dt. We are now going to integrate also the right hand side to give us integral dr over r is equal to minus k integral dt. And finally, that gives us natural logarithm of r is equal to minus kt plus arbitrary constant c. When exponented, we discover that the radioactive substance itself, r, is equal to exponential minus kt plus arbitrary constant c when we use the laws of logarithm and exponential evaluation based on indicial or power function to relate the evaluation, so that therefore the radioactive substance, which is a function of time, is equal to exponential minus kt plus arbitrary constant c. It can be furthered, but that is to say, we would have to be given the IVP, the initial values. Now, perhaps at a particular point where the radioactive substance starts decaying.